Hi everyone. In this video, we are going over quiz 5. So the average was 78%, which was really good. The average time was about 18-ish minutes. So again, seems to be like you're using your time efficiently. So just make sure you're reviewing the questions you're getting right and wrong so that we don't have repeat mistakes, especially when it comes to the exam. All right, question 1. What components are present in every substitution reaction? So every substitution reaction has our nucleophile, our electrophile, and our leaving group. So those are the correct statements. Carbocation reagents are in some of our SN1 reactions because when you get a carbocation, you have to watch out for that. Just like with the hydride shift, those are with some SN1 reactions because that's a type of carbocation rearrangement. Pi bonds, that's only the product of elimination is where you get the pi bonds. Question 2. Out of the possible structures below, give the major product of the following reaction. So for this one, you only have substitution structures. So essentially, I'm trying to get you to say, all right, what would be the major of the substitution products? So what is the major substitution that could happen? So that means if your only options are SN1 or SN2, which one would happen here? So what I wanted you to recognize is that you have a weak nucleophile and a tertiary leaving group. That tells you you're doing SN1. So you're going to have your substitution at that tertiary location so that you would make that tertiary carbocation. Ethanol comes in. You would get your protonated product that then you just need to deprotonate in order to get it to be neutral. And because it's acid-base, it's in equilibrium. So that would give you your tertiary carbocation. So if you had had a rearrangement to form the secondary carbocation, that would form the top product. If you had a rearrangement to a primary carbocation onto this methyl, then that would give you that bottom product. So we will never, never, ever, ever go from a more substituted or a more stable to a less stable carbocation. We're never going to make a less stable carbocation. So there was no reason to do a hydride shift here. It just was leaving group gets replaced with the nucleophile. It was that simple here. Question 3, rank the molecules from fastest to slowest for a unimolecular substitution. So that's SN1. So SN1 only cares about our substrate. So the nucleophile doesn't come into play. So it's just looking at the substrate, which actually that's all we have to compare here anyway, is just the substrate. So what we care about is that substitution pattern where we're looking at the carbocation stability, where it's tertiary, it's going to be more stable than secondary, which is more stable than primary, and it must be sp3. So if I'd had double bonds, then I would have to consider that. There are no double bonds here, so I don't have to worry about that. But if you had a double bond, it'd be even slower, so that your primary would still be faster than, say, that vinylic chloride. Like that's super duper unstable. So that's going to be even slower. Because this is really destabilizing, having that carbocation on an sp2 hybridized carbon. So then we're just looking, all right, tertiary is going to be more stable than secondary, which is more stable than primary. And so then that's the order that we get. That's the fastest, that's the slowest. Question 4. The rate determining step for the following reaction is, all right, so looking at this, there are kind of two things to consider. One, we've got to figure out what's actually going on. So we got to know what reaction we're doing. Two, then we got to understand what are the words here? What are they saying? So starting out, I see, let's just figure out what has to happen and then worry about the words. So starting out, I have an alcohol, I have butanol and hydrobromic acid. I see a strong acid. That means protonate something. So my alcohol is going to become protonated with the hydrobromic acid. We do that acid-base reaction. That creates that oxonium ion, the really good leaving group that bromide, which is now a nucleophile only, can do substitution. So because of the fact that the bromide's nucleophile only, that tells me SM1 versus or SM1 or SN2, also I know I'm forming a substitution product, so I knew it had to be SN1 or SN2. And then it's just the fact that this is a primary leaving group. That's what tells me it has to be SN2. You will not make a primary carbocation. You must do SN2. So then that is going to be our slow step. Because remember, acid-base chemistry is always really fast. It's really easy to just move protons around. That is kinetically favored. The SN2 reaction, that is the rate determining step, is the substitution step. So this is the slow step. That is the rate determining step for this reaction, is the actual substitution part of it. So now let's go through and consider what do each of these statements mean and which one describes that SN2 reaction. So the first one says ionization, meaning I'm going to make ions, break bonds, of the alcohol to give a carbocation. So that means that I'm starting with my alcohol and I'm just going to take those electrons and give them to the OH to make a carbocation. So that definitely does not describe what's going on there. Also, OH is a bad leaving group, and we are not going to make a primary carbocation. So that's definitely not what's happening. So not only does it not match what we needed it to, we're definitely not going to have OH just leave and make a primary carbocation. That's bad for two reasons. All right, then we get loss of water from the protonated alcohol to give a carbocation. So that's saying loss of water from the protonated alcohol. So that's starting from that oxonium ion, having that just ionize. So then that would be, if this was an SN1 reaction, that would be the slow step, is loss of the leaving group is the slow step for SN1. And water can be a leaving group, but we are not going to make a primary carbocation. So although this is a good leaving group, so you could do SN1 here, not on a primary. So if this was a secondary or a tertiary, then absolutely, that would be your slow step, especially for tertiary. But that's not what's happening here. We're primary. We have to do SN2. So that's incorrect. Next, capture of the carbocation by the bromide anion. This is the second step of the SN1 reaction. That will always be faster than the first step. Formation of a carbocation is always slower than having the nucleophile attack. So that is not the correct step, even if we were doing SN1, but we're not doing SN1, so that's also doubly wrong. Displacement of the water from the protonated alcohol by the bromide ion. So that's saying that I am displacing, meaning replacing. So I'm kicking it out, displacing it by the bromide, or displacing that water, which is from the protonated alcohol, by the bromide. That is my SN2 reaction. So that is correct. That is the correct answer. That is accurately depicting in words what is happening in those arrows. Lastly, we have protonation of our alcohol. That is the first step of our mechanism, but acid-base chemistry is always really fast. So this is definitely not going to be our rate determining step. This isn't the slow step. It's actually the fast step of our reaction. It does happen, but it happens quickly. Question 5, which of the following will undergo SN2 mechanism the fastest? All right, so for SN2, we care about our substrate and our nucleophile. Those are the two things of the SN2. So for substrate effects, we care that primary is going to be faster than secondary, which is way faster than tertiary. And for our nucleophile, having a strong nucleophile, negative charges, is going to be better than being neutral. So stronger the nucleophile, faster the reaction. All right, so now let's go ahead and draw out what each of these look like. So 2-bromopropane and water here. This is a secondary leaving group and a weak nucleophile that can be SN2, but it's going to be pretty slow, having the sterics of a secondary and a neutral nucleophile. It's not a very fast SN2. Can be SN2, but it's not going to be very fast. 1-bromopropane and hydroxide. So that's a primary leaving group with a strong nucleophile. That's going to be a very fast SN2. That's definitely faster than this. It has less sterics and you have a stronger nucleophile. That's faster for two reasons. 2-bromo-2-methylpropane and water. That's a tertiary leaving group and a weak nucleophile. That is not going to be SN2 at all. Having that tertiary, it's way too slow. It's too sterically encumbered. We will not do it. It will be SN1, but definitely not SN2. 2-bromopropane and hydroxide. So that's the secondary leaving group and the strong nucleophile. Could be SN2. definitely faster than the top one because now I have a stronger nucleophile. So it'll be a faster SN2, but it's not faster than being the primary with the strong nucleophile. So that one is definitely the best answer. 1-bromopropane and hydroxide. Question 6. What is the major organic product of the following reaction sequence? Note one equivalent means you only have one of those molecules for each reactant. Okay. So starting out, I see my thiol and potassium hydroxide. So when I look at this, remember potassium hydroxide is a strong nucleophile, strong base. So when I look at my thiol, that thiol, yes, it is primary. So hopefully you recognize that we're not going to do an E2, but this is a bad leaving group, right? This is a really poor leaving group. So I can't do substitution. But that hydrogen is acidic. I have a hydrogen on an electronegative atom. And we already said potassium hydroxide is a strong base. So the first thing that we're actually going to do is an acid-base reaction. Your hydroxide is going to deprotonate the thiol to make the sulfide, to give you that S minus, which is now a strong nucleophile, which makes a little bit more sense for our second step, because in our second step, we're adding that iodomethane, which is a very good electrophile. It's not even primary, it's a methyl electrophile. So this is really sterically unencumbered with a great leaving group. That's going to do SN2 really quickly. So having a strong nucleophile with that really good electrophile is just reinforcing we're doing SN2. So that kind of tells you that like the first step is definitely doing acid base because all it's doing is making a faster SN2. And so then we get to this product where you have 4 carbons on one side, the sulfur, and then 1 carbon on the other end of your thioether. So when we look at our different products, the first one requires the loss of 3 carbons. We have no way of losing those 3 carbons. Carbon is not going to be a good leaving group. So there's nothing that we can do there. That is definitely not going to be the correct product. We have no way of losing all of those carbons. It did incorporate the sulfur, which is good, but we have no way of losing carbon. So not that one. We have no source of nitrogen here, so I'm really glad you recognize that that element is not anywhere in here. So no one picked that one, which is fantastic. That is definitely a wrong answer. If you don't have the element, you didn't do the reaction. The next one, I see my 4 carbons, then the sulfur, then the 1 carbon. That is the correct answer. That is my thioether. Next one down, I see 6 carbons and then the alcohol. So that would require you to do an SN2 reaction to get an OH and then lengthen your carbon chain on this side so that you're adding a carbon to the other end. Remember, we're only going to have reactions occur at our polar bonds. So there's no way for us to lengthen that carbon chain. So this is definitely also a wrong answer. So the last one would be the next best answer, although it's still wrong because it forgets the fact that hydroxide can just be a base and just deprotonate any acidic proton, and that our thiol is not a good leaving group. So this would be if you just make a normal ether and you just do SN2 in the first step, but we're not doing that because that SH minus, that's a bad leaving group, just like OH minus is a bad leaving group. So we're not going to do that reaction either or make that product either. So it's going to be the thioether. That is the correct answer. Question 7. When R3-bromo 3-methylhexane is treated with water, a racemic mixture of 3-methylhexane 3-ol is produced. By what mechanism does this reaction occur? So you didn't even have to read any of those words, really, except for racemic. As soon as you see racemic, that's SN1. You're done. It's just, that's it. That's the only way to get a racemic product, SN1. But we can also double check ourselves to be confident that it is SN1. The fact that I see that I'm making an alcohol, not an alkene in the name, reinforces that I'm doing substitution, not elimination. So remember, elimination makes alkenes. It would have to be like a hexene, not that hexanol. So definitely can't be E1 or E2. And then the fact that this is a tertiary leaving group with a neutral nucleophile, that's definitely going to be that substitution. So I know that it is SN1. because of the tertiary leaving group, and the fact that it was racemic is really reinforcing the fact that I went through a carbocation intermediate. Question 8, rank the following alkenes in order of decreasing stability. So remember that how we rank our alkene stability is first you consider substitution, then you consider sterics. So our monosubstituted is less stable than di, which is less stable than tri, which is less stable than tetra. Then I consider sterics. So my 1,1 disubstituted is less stable than cis, which is less stable than trans. And in general, Z is less stable than E. So now let's look at our actual molecules. If we draw each of these out, I get these alkenes. The first one, this is tri-substituted, meaning I have 3 non-hydrogens attached and 1 hydrogen directly attached to the alkene. So it's tri-substituted. The next one is di-substituted, then mono, and then the last one is tetra-substituted. So that immediately says tetra-substituted, that is fastest. Then my tri followed by di, and then mono will be my slowest or least stable. Sorry. Sorry. Question 9. How many degrees of unsaturation does the following molecule contain? Remember, each unsaturation is a ring and a pi bond. So this has 1 ring, 2 pi bonds. That is 3 unsaturations. So if you selected 2, make sure you're watching out for the fact that a triple bond contains 2 pi bonds. So that is 2 unsaturations for every alkyne. Question 10, choose all the answers that are true. So what is the major product of an E2 reaction with that hindered base? Hindered meaning sterics, meaning bulky base. So that's going to be an E2 reaction with a bulky base is going to be the Hofmann product. So it will only arise from an anti-periplanar configuration. That is true for every E2 reaction. So that's absolutely true. Have scrambled stereochemistry at the site of the reaction. Scrambled meaning mixed. So that would be racemization is what that's saying. So that's saying SN1. For the Hofmann product, yep, that's E2 with a bulky base. So yes, tick, that's the correct answer. Zatsev product, that'll be either E2 with a non-bulky base or any E1 reaction. So that's not what we have here. Have inverted stereochemistry at the site of the reaction. That's incorrect. That was SN2, is that inversion. All right. Please let me know if you have any questions, and I hope you have a wonderful day. Bye.